From the first equality, we also know that lambda 0 is 0. This is important. Because the left hand side, if k is 0, the left hand side is 0. So the right hand side must be 0 because a0 is 0, so lambda 0 must be 0. Okay? And also we might assume from the limit of eta is 0. From this, we might also assume that eta h is not greater than h. Okay. Otherwise, you decrease the r. This must be true. If this is not true, you might decrease r to make it true. So this is the basic property of limit. The limit is 0. 0 is less than 1. So eventually, the quotient, the norm of the quotient will not greater than 1. Therefore, this means the norm of eta h is not greater than the norm of h. So this is our preparation. Now, we will study the differentiability of the composition. So we need to compute a plus h. Minus a. We need to compute this. So we apply k. We use the to estimate this. This is a thing we have to do because by definition, differentiability of the composition. To study the differentiability of the composition, you need to study this difference. So the idea is to use the this equality. Use the equality for f, which the special k. We take k to be. We take k to be this. We take this to be k in the previous equality, the box equality, and we see what happened. Okay. So our choose k, take k to be the ga plus h minus ga, which is also from the second equality here. This is also bh plus eta h. We obtained f g a plus h minus f g a. This is the value of f at g a plus h. G a plus h. G a plus h is nothing but G a plus k. G a plus h is G a plus k. Our k is here. Okay, so this is nothing but G a plus k. G a is b, so this is b plus k. Okay, so we will not go this way. So this is fb plus k. Similarly, fga is b, therefore this is fb. So by the first equality, this is a k plus lambda k, right? fb plus k minus fb is ak plus lambda k here. Okay, once k is small, so if h is small, then k will be small by the continuity of g. You see that if h is small, then k is small. Therefore, eventually this equality will be true. So we have this. This is a k is g. K is ga plus no, sorry. K, now we use K equals BH plus eta H. So this is BH plus eta H. This is AK plus lambda K, also BH plus eta H. Okay? And we split this term to be ABH plus A eta H plus lambda BH plus eta H. Okay? We get this result. So our difference of the composition at 2 points equals some matrix independent of H equals some matrix multiplied by H. Okay, some matrix multiplied by H here, and a remainder term is here. The remainder term has 2 parts. The first part is A eta H. The second part is lambda. Okay, so if the remainder term divided by H goes to 0, then this by definition means that the composition is differentiable at the point A, and the derivative is AB. AB is precisely f point B, g point A, and the theorem is proved. So we only need to prove that the remainder term divided by the norm of H goes to 0 as H goes to 0. Okay? Now, for the remainder term, we consider the first part. The first part is easy. The first part, we study it here. A eta H divided by the norm of H. For the A eta H, the norm of A eta H will not greater than the metric norm of A and the norm of eta H divided by the norm of H. But because our eta satisfies this condition, here, the eta H divided by the norm of H goes to 0. Therefore, the norm of eta H divided by H is also goes to 0. So this goes to 0. This goes to 0. So we conclude that this goes to 0. So our remainder term, the first part of the remainder term is good. Divided by the norm of H goes to 0. So it's sufficient to prove that the second term also has this property. So it's sufficient to show H goes to 0, lambda BH plus eta H divided by the norm of H is 0. Okay? So to prove this, firstly, we have lambda. We have two facts. Firstly, is lambda 0 is 0. We emphasized this previously. Lambda 0 is 0, and the limit k goes to 0, lambda k divided by the norm of k is 0. From these two facts, for any epsilon positive, there exists a delta positive such that for k small, k in Rm, the norm of k less than delta, we have the norm of lambda k divided by the norm of k will not greater than epsilon. That is, lambda k will not greater than No, not epsilon. I need to adjust a little. Less than epsilon, the norm of the matrix B plus 1. I add this factor for later purpose. Okay, so this inequality can also be written in this way: lambda k less than epsilon b plus 1 norm of k. This inequality is true from the limit 0. From the limit is 0 from this condition. This inequality is true for k not 0. But because lambda 0 is 0, and this inequality is also true when k is 0. Therefore, we can remove the requirement that k is not 0. So this can be removed. So this is true for every k once the norm of k is less than delta. Okay. Now this is the first point. The second point, we note that limit h goes to 0, the norm of b multiply the norm of h plus the norm of eta h. Of course, this is 0 because eta h goes to 0. Not only eta h goes to 0, eta h divided by the norm of h still goes to 0. Okay, so of course we have this limit. From this limit, apply this limit to the delta we obtained in the last step. Apply the limit using this limit and consider the delta we determined in the previous step. This delta, what we get, we see that for the delta, we have a low positive, such that if h in Rn, norm of h is less than rho, we will have BH, no, okay, BH, maybe I will not jump, B H plus eta H is less than delta. Okay, because the limit is delta. Eventually, when h is small enough, it will less than the delta given previously. Okay, so what this means? We consider B H plus eta H. This is not greater than the norm of BH plus the norm of eta H. And the norm of BH will not greater than the metric norm of B multiply the norm of H plus eta H. So this will less than delta. Okay, once the norm of H is less than rho positive. Okay, of course this is also true when h is 0. Therefore we don't need to write h the norm of h to be positive. This is true whenever the norm of h is less than